Why would Intel put a $400 million, 165-ton machine on the production line for its newest laptop chips? Because this machine can draw details that ordinary light cannot reach. It fires lasers at falling drops of tin, creates light that air itself will absorb, and guides that light across mirrors whose defects must be measured in atoms. ZEISS says some of those mirrors can take roughly a year to make. ASML says shipping one of its EUV systems can require 40 freight containers, 3 cargo planes, and 20 trucks. But the most extraordinary fact is not the price, the weight, or the physics. It is that only one company currently builds commercial EUV lithography systems, ASML, and in July, ASML announced that Intel had moved its next-generation High-NA machine into high-volume manufacturing for selected layers of a subset of Panther Lake processors. The race for smaller chips, more powerful AI, and national technological power now runs through a machine with no commercial rival. So how did one Dutch company become this difficult to replace? Modern processor is printed layer by layer onto a silicon wafer. Lithography projects each microscopic circuit pattern. Extreme ultraviolet lithography, EUV, uses light with a wavelength of 13.5 nanometers. Ordinary glass absorbs it, and so does air. The light must travel through a vacuum and bounce across mirrors instead of lenses. High-NA is the next step. NA means numerical aperture, the optical system's ability to gather light and resolve smaller details. ASML's new platform increases that number from 0.33 to 0.55. The company says its EXE5200B supports 8 nanometer resolution, prints features 1.7 times smaller, and could enable 2.9 times the transistor density of its earlier EUV platform. It does not manufacture a finished chip by itself. Its value is precision, printing critical patterns with fewer exposures and potentially fewer costly process steps. The process begins with molten tin. Inside the source, microscopic droplets fall through a vacuum chamber. One laser pulse reshapes each drop. Another turns it into plasma. That plasma emits EUV light. The beam is collected, reflected, shaped, and projected through an optical path with almost no tolerance for contamination or vibration. ZEISS exclusively supplies the optics used by ASML's EUV machines. It says high-NA illumination contains more than 25,000 parts, while the projection optics contain more than 40,000. This is the first correction to the one-company story. ASML integrates the system, but specialists solve different pieces of the impossible problem. ZEISS Optics in Germany, light source technology developed through Cymer in the United States, and final system integration in the Netherlands. The monopoly is real. It is also distributed. If a machine costs around $400 million, why has a competitor not built another one? Because money is only the entrance fee. The real barrier is accumulated knowledge. ASML says EUV required more than 2 decades of development. A rival would have to master lasers, optics, vacuum systems, sensors, software, contamination control, and precision motion at the same time. And it would need a supplier network capable of producing every critical component repeatedly, not once in a laboratory, but at factory reliability. ZEISS says roughly 2,000 of its employees work on high-NA technology. The system used to measure its mirrors weighs around 150 tons and operates inside a vacuum chamber roughly 5 by 10 meters. A competitor would also need the trust of chipmakers. A failed scanner can delay an entire production ramp. The strategic asset is therefore not one patent or one factory. It is a web of capabilities that took a generation to assemble. Intel received the first high-NA system at its Hillsboro research site in 2024. In July 2026, ASML said Intel Foundry had entered high-volume manufacturing for a subset of Core Ultra Series 3, Panther Lake, using high-NA for selected product layers. That distinction matters. The entire processor is not printed by one high-NA machine. Selected layers were qualified on both conventional EUV and high-NA, allowing Intel to compare the manufacturing routes. Reuters reports that high-NA equipment costs around $400 million, roughly twice the price of standard EUV. A chipmaker must decide whether fewer patterning steps, better process control, and future scaling justify the scanner, cleanroom space, installation, and redesign. Being first can create an advantage. It can also make you pay for the learning curve. Intel is not merely buying a machine. It is buying time to learn before the next manufacturing race begins. Physical scale reveals how unusual this business is. Intel described its first high-NA system as weighing about 165 tons. ASML says a typical EUV system contains around 100,000 parts. Shipping an EUV machine can require 40 containers, 3 cargo aircraft and 20 trucks. Those logistics describe EUV systems generally, not the exact packing list of every high-NA shipment, but the lesson is clear. Machine does not arrive, an industry arrives. Modules travel under controlled conditions. Cleanrooms require special foundations, utilities and environmental stability. Installation teams assemble and calibrate equipment that moves wafers quickly while preserving nanometer-scale alignment. ASML says the EXE5200B can process at least 175 wafers per hour. Customers are not paying only for precision. They are paying for precision at production speed, the difference between a scientific achievement and a factory tool. Once one supplier becomes essential, the machine stops being only a technology story. It becomes foreign policy. The Dutch government requires export authorization for specified advanced semiconductor manufacturing equipment, including lithography-related technology. It says decisions are made case by case, and the rule is not a blanket export ban. But the principle is unmistakable. Access to chip-making tools can influence which countries and companies build the most advanced manufacturing capacity. That gives ASML extraordinary importance, but not unlimited power. ASML depends on governments, licenses, customers, and suppliers. ZEISS depends on its own specialist network. Chipmakers depend on maintenance, spare parts, and continuous upgrades. Concentration can be efficient because the best specialists focus on what they uniquely do. It can also be fragile because one critical link cannot be replaced quickly. $400 million machine is not powerful because one company owns every component. It is powerful because no rival has reproduced the entire system behind it. Intel has moved High-NA into selected production steps. IMEC received another advanced High-NA system in 2026 for sub-2 nanometer logic and high-density memory development. The next generation of computing is moving from experiment toward manufacturing. And that leaves one uncomfortable question. If the world's most advanced chips depend on a machine only one company can sell, and on a network nobody can quickly rebuild, what happens when one link breaks? This is where the billions go, into machines that do not merely make technology. They decide who gets to make it next.